Hello everyone, welcome to lecture 27 of the online course Modern Display Technologies Flat Panel Display. Today's lecture will be on classification of transreflective LCDs. Here is the lecture outline. We'll have 4 classifications mechanism for this transreflective LCDs. The first one is absorption type, where we'll discuss about the nematic and the cholesteric absorption transreflective displays. Then we'll look into the scattering type and scattering plus absorption kind of transreflective LCDs or LC gel designs. And then we will look into the reflection type, okay, where the cholesteric with image enhanced reflectors, that is IER, are used. And then if time permits, we'll cover this, or else we'll cover this in the next lecture, that is the phase retardation type designs, okay. And then we will be comparing the absorption, scattering and the reflection types. Finally, we'll provide a summary and a bridge to the next lecture, where we'll be covering this particular phase retardation kind of design. So once you want to classify the transreflective LCDs, okay, there are basically, you need to understand the transreflective LCDs are nothing but reflective LCD style liquid crystal layer, plus you have a transreflector that is basically combined inside one particular crystal. So the classification is basically done based on how the liquid crystal layer is modulating light. So that is mainly by the light modulation mechanism, and through that the transreflective LCDs can be divided into 4 categories. The first 3 types are like absorption, scattering and reflection types, which will be covered in this lecture. So these 3 do not basically modulate the phase of light. As you can understand, these are basically on the amplitude, right? So they absorb, scatter or reflect light, okay, and in this case 1 or 0 polarizers is preferred for getting high brightness. And the 4th category is based on phase retardation, which we will be covering in the next lecture. So this basically modulates the phase of the transmitted or reflected light. So it basically needs 2 polarizers, but it dominates current commercial products mainly because of the high contrast and the low voltage driving voltage requirement it can offer, along with the manufacturing compatibility. So now let us focus on the absorption type transreflective LCDs first, which are based on the guest host principle. So what is this guest host mechanism? So in a guest host liquid crystal mixture, rod shaped dichroic dye molecules, which are basically the guest, are dissolved into the nematic liquid crystal, which are the host, at a low concentration, typically by an 2 to 5% weight, okay. Now because these dye molecules are elongated and they tend to align with the surrounding liquid crystal director, okay, so this kind of effect is called guest host effect, okay. And reorienting the liquid crystal director with some applied electric field will basically physically drag the dye molecules also along with it, so they also get aligned with the electric field, okay. So how the switching works here: as the electric field reorients the liquid crystal director, the elongated dye molecules also follow it because they get dragged by the liquid crystals, okay. So this dye basically absorbs strongly when its axis is parallel to the light's polarization, and they absorb weakly when the axis is perpendicular to the light polarization. So you actually see a voltage controlled absorption, okay, in this entire mechanism, and no phase retardation or polarizer rotation is required in principle. So what you get here is something called the dichroic ratio, that is the ratio of the parallel to perpendicular absorption coefficient. So here alpha stands for the absorption coefficient, and the ratio of it gives you the dichroic ratio, and it is a key figure of merit that sets the achievable contrast ratio from this kind of displays. Now it also comes with some practical limitation. Typical contrast ratio only 5:1 with around 40 to 50% reflectance is achieved using this kind of method. So you can see this is limited mainly by the dye's dichroic ratio, and the long term photostability of the dye also remains a concern. So only you will see a very few guest host kind of LCDs have made it to the market. So in this particular slide, we'll look into the nematic absorption transreflective display, and we will discuss about the dark state. So you see the figure here. This particular device combines a half mirror metal transreflector, which is basically coming from the previous lectures amplitude splitting family, along with two quarter wave plates. Okay, so one is positioned on either side of the transreflector, right? So the transreflector is basically getting sandwiched between these two, and then you have a homogeneously aligned liquid crystal layer doped with the dyes. Okay, so you can basically, the black ones can be the dyes. Okay, so you can see it is basically the guest host kind of principle that we have discussed in the previous slide. Okay, now how it works in the voltage off state, that is in the dark state. Okay, so let us talk about the reflection mode first in details. So let us start with unpolarized ambient light entering from the front. So this is the front of the display. Okay, so it basically passes through the homogeneously aligned nematic liquid crystal of the dye layer. Okay, so which, because of the dye molecules are aligned along the rubbing direction, they basically linearly polarizes the light via directional absorption, because the light polarization along the dye's long axis will get absorbed. Okay, and the orthogonal direction will get passed through. So you are basically getting a particular preferred polarization out of this. Okay, so you get a linear polarization. Now this linear light then passes through the inner quarter wave plate. Okay, this one, and it basically converts it into a right circular polarization, and then it reaches to this particular transreflector, where it gets reflected off the transreflector surface, and this reflection basically introduces a pi phase shift or 180 degree phase shift that basically flips the handedness to the left circular polarization. Now when this left circular polarized light passes through the same quarter wave plate, okay, it basically passing it through the second time, then it again gets converted into a linear polarization, but the polarization axis will now get rotated to the parallel of the liquid crystal of the dye alignment direction. So what happens in that case, the dye will basically absorb it strongly in the second pass when the light is trying to come out. So you don't get any light out here, so it is becoming completely dark. So that is how it works in the reflection mode. Now let's see how it works in the transmission mode. In the transmission mode, you have a backlight at the very back. So the backlight is entering from behind, so it will follow the mirror image version of the same path, okay, through the outer quarter wave plate. So you have a polarizer, so it gets polarized, and then you have this quarter wave film that basically converts linear to circular polarized light, okay, and then it gets transmitted through this one, and finally when it gets again rotated to the linear polarization, that basically changes the polarization axis, okay, it becomes orthogonal. So that basically gets absorbed by this particular liquid crystal or the dye assembly, okay. So what you see here is that there is a symmetry is exactly what it makes the voltage off state a clean and well matched dark state in both the modes simultaneously, and this is one of the major goals of the transreflective pixels. Now what happens in the on state? In the bright state, the liquid crystal and the dye reorient nearly perpendicular to the substrate. So in that case, minimal absorption will happen and there is no polarization change in either mode. So what you get is nothing but a bright output with very little attenuation in both R and L modes. Now there is always a dilemma about the placement of the transreflector. So the inner quarter wave film, if it is placed inside the cell alongside the transreflector, that must survive the polyimide alignment layer curing bake process, where you basically need to expose it to 250 degrees centigrade for over an hour. So that is a challenge for a polymer retarder film. So what is the practical resolution to this problem? The external or outside cell placement is basically preferred to protect the film from this kind of high temperature process step, and that is why you have seen that the liquid crystal cell is basically between the two ITO or transparent electrodes, and the polarizers and the quarter wave plates and everything is placed outside. Now cost of this kind of solution is that when you are placing any optical element outside the cell rather than inside, just next to the liquid crystal layer, you are basically introducing a spatial offset between the incoming and the outgoing light paths at some oblique angles, or at any oblique angle for the matter. So what you will also see the parallax problem. So these are basically, these will all be examined in full detail in the next lecture, not in this one. Now let us move on to the next type, that is the cholesteric absorption reflective display. Okay, so here this particular figure shows a half mirror transreflector plus a single quarter wave film which is placed outside the cell, and then you have this cholesteric liquid crystal and dye mixture placed between the ITO electrodes, and you have a backlight here. So this is basically similar kind of a assembly that you have seen earlier, but this cholesteric variant of the guest host transreflective display, which is engineered specifically to solve the transreflector placement dilemma which was raised in the previous slide. Okay, so here you are basically removing one of the quarter wave films, as you can see. Okay, so what is the main advantage here? So by replacing the nematic liquid crystal host with a cholesteric liquid crystal, which is basically a chiral nematic, right? So in this case only a single quarter wave film is required overall. So it can be positioned between the transreflector and the outside linear polarizer. So it is basically entirely outside the liquid crystal cell. Now because this is now the only retarder film in the cell or in the stack, it basically sits outside the cell, and the transreflector itself is basically freed up to be placed inside the cell itself, just next to the liquid crystal layer, okay, without needing to protect a polymer retarder film from the baking process or the curing bake process that we discussed earlier. So this basically eliminates the parallax problem also, okay, because the parallax arises especially from a spatial offset between where light enters and exits the pixel and where it is redirected, or you can say reflected, by the transreflector. When there is a thick layer like a substrate between the liquid crystal switching layer and the transreflector. Since this particular design keeps the transreflector directly inside the cell, okay, so, or you can say immediately adjacent to the active liquid crystal dye layer, there is no such offset and no parallax that occurs. So that basically directly solves the problem which the previous nematic design was facing. So now let us see how this voltage off or the dark state is obtained. So in this case, the voltage off state, the cholesteric liquid crystal dye layer is in its right-handed planar helical texture. So in the case of R mode, you can consider the unpolarized ambient light is getting heavily attenuated simply by passing through this absorbing helical structure twice. So there are one path is going in, another path is coming out. Okay, so it is getting almost completely dark in the reflection mode. In the transmission mode, what is happening, the backlight becomes right-handed circularly polarized after this polarizer, okay, and this quarter wave film is there, and it is that is where it is getting right-handed polarized or right circularly polarized, and this is attenuated further by this transreflector, and this weak right-handed light is then strongly absorbed by this same handedness cholesteric dye layer, okay, because this is where this thing is coming from. So here the elegant point is that the circular polarized light of the same handedness as the cholesteric helix is. So in that case, the light and the cholesteric structures interaction becomes very strong, okay, and that's why the absorption takes place. So this kind of concept, tying this design back to the Bragg reflection physics that we have seen in the lecture 26, cholesteric reflector. On the other hand, the voltage on or the bright state is much simpler. There the liquid crystal and the dye basically reorient perpendicular to the substrate, okay. So in that case, negligible absorption takes place and you will see high reflectance in R mode and high transmittance in T mode. So you will also notice that both the guest host design that we have discussed in nematic and cholesteric, they share the same fundamental sealing with practical dyes, giving a dichroic ratio of around 15:1, that will still cap the contrast ratio to only 5:1, which is low and it is inadequate for high-end color displays. Hence, this kind of absorption type of design occupy only a very small or niche area of the handheld display market. Now we move on to the next type, which is the scattering type transreflective LCD, okay. So here this is basically based on a liquid crystal gel, okay. So this is a liquid crystal gel kind of device. So here you see the schematic of this liquid crystal gel, plus you have two quarter wave plates, you have a transreflector, okay, and you have this polarizer and the backlight, okay. So that basically this polymer network that you see here, okay. So these are the substrate and this is where the liquid crystal gel is, okay. So this polymer networks basically confine the homogeneously aligned nematic liquid crystal like this, okay. So here the important part is this cell that starts as a mixture of nematic liquid crystal and a reactive monomer, which is filled into a cell with homogeneous planar unidirectional surface alignment. Now exposing this kind of a mixture to UV light triggers polymerization of the monomer, which will basically form permanent solid polymer network running through the liquid crystals, while the surrounding liquid crystal molecules remain free to reorient under the application of any electric field. So this particular composite structure is called a polymer stabilized or LC gel system. Okay. So let us try to understand how the voltage off or the bright state looks like. So when no field is applied, the liquid crystal basically stays in its original uniform homogeneous alignment. So the cell is optically clear with no scattering centers. Now in the reflection mode, the unpolarized ambient light simply passes through this transparent layer, reflects off this transreflector and returns largely unpolarized and unattenuated. So you basically get a bright reflective state. However, in the transmissive mode, what happens? You basically see the backlight, it becomes a linearly polarized P wave after the polarizer. Okay. So this is basically in the voltage off case, this is in the voltage on case. Okay. So for the voltage off case only we are discussing. So you see in the transmit mode, this backlight is basically becoming a linearly polarized P wave after the polarizer. Okay. And because the two quarter wave plates are there on either side of the transreflector, which are oriented with perpendicular optic axis, their combined effect on a linear P wave basically cancels out. So the P wave passes through the transreflector, okay, and exits the display still linearly polarized and largely undiminished. So you are basically getting a bright transmissive state as well. Now let us see what happens when you apply voltage. Okay. Now when you apply sufficiently large voltage, that basically exerts a reorienting torque on the liquid crystal molecules, which can be seen here in the second figure. Okay. So what is happening, because you are applying very large voltage, these molecules are basically mechanically constrained by the surrounding polymer network, so they cannot switch uniformly. So what they will do, instead they will break up into small misaligned microdomains, okay, strung along this polymer chain. And when these domain sizes are comparable to the wavelength of the visible light, they strongly scatter the extraordinary ray, while the ordinary ray can still pass through unaffected, producing a hazy, translucent and not completely black dark state. Okay. So this is what you basically see here. Now what is the advantage of having a single polarizer for the brightness? So just like the absorption type design, the scattering design basically needs only one linear polarizer. Okay. As you have seen previously also, in the whole stack there is only one polarizer. So a much larger fraction of the incident light budget survives to reach the viewer, because if you put another polarizer, that basically reduces another 50% of the light falling on it, or even more, because it only polarizer only allows one particular polarization, not 50%, major chunk you can say, giving this. So when you have only one polarizer, that allows you to have more brightness from this kind of designs. So now let us look into some practical drawbacks of this scattering type liquid crystal gel designs. So here we will basically talk about the three specific engineering problems that limit the pure scattering type liquid crystal gel design from the previous slides. Okay. So that will basically set up the motivation for the hybrid kind of designs which are based on scattering and absorption, which will be covered next. So what is the drawback 1? So you can understand the first drawback is a weak dark state, because the scattering gives you a translucent, not black dark state. That means the contrast ratio is low, and it depends heavily on the viewer's distance from the panel. So what is the partial fix to this problem? You can dope the liquid crystal gel with a small amount of black dye that can improve the dark state, but the contrast remains limited by the dye's dichroic ratio, which we discussed earlier. Second drawback is the parallax. So inserting the first, or you can say the inner quarter wave film, will reintroduce the same parallax problem that was seen in the nematic absorption type display, which is already discussed. The third drawback is the high driving voltage. So the polymer network constraint typically pushes the required drive voltage to be above 20 volt. Okay, so that is beyond what the standard thin film transistors, those used in LCDs, are able to supply. So what is the net verdict here is that when you put all these three drawbacks on the table, you will see that these are enough to prevent only scattering type transreflective LCDs to become a wide commercial success. So with that, we conclude this lecture. We'll cover the remaining topics of this lecture in the part B of this lecture. Okay, thank you. If you have any queries, you can drop an email to this email address.